a look right now at what logarithms are all about. The basic concept of logarithms is it's the exponent that when a number is raised to that exponent, it equals another number. As an example, we have the number 100 here. So 100 is equal to 10 to the second power. The 2 is the logarithm of 100. We would actually write that as the logarithm base 10 of the number 100 is the exponent that this base number needs to be at. So 10 squared equals 100, you know is true. That can be written in this form as log base 10. Oops, I want that 2 to go away. Log base 10 of the number 100 equals 2. So these are equivalent expressions. But this one is logarithmic. That's a logarithmic expression. And this one is an exponential expression. Exponential. Good. And you can move them interchangeably. Right? And we'll go over that at some point too. But notice that that 10 goes over to the 2 and pushes the 2 up to be an exponent. And log goes away, but 10 to that power equals the 100. Now, let's take a look at some other examples of it on here. In fact, let's go down to the bottom of this number line. And here's where 0 is. And right about here would be the number 1. Well, we know that anything to the 0 power is 1. And then, of course, 10, and anything to the power of 1 is equal to itself. Well, between 10 and 100, we have 90 numbers, but we go from the exponent 1 to the exponent 2. The concept here is that you can put any number here in terms of 10 raised to a certain power. Unfortunately, they'll all be rounded. So we have to round these, and we usually go like 4 decimal places, although in this case, let me see, I'll do them with a calculator here on them. Okay. So first thing is we're going to see where 10, I want to see where is 10 to the 1.5? Where's the midpoint of it? So 10 raised to the power of 1.5 is about 31.6. Now, the exact halfway point between 10 and 100 would be the number 55. We'll put a 55 here. But if we do the log of 55, well, the interesting thing is that we don't get a 1.5 exponent, okay? What we get is we get 10 to the 1.7404. Logarithms are done 4 decimal places unless there's a compelling reason not to. So I'll do 1.7404 here. Now, although it would make sense to round it to 1.7, but we'll leave it with the 1.7404 right there. Right now, we're just doing as exponents. So the actual 0.5 or so is about at where 32 is. It's a little under 10 to the 1.5, but it's close enough. In fact, the log of 32 is 1.5051. Very, very close. Now, the reason why, let's actually do a couple others. Like there's log of 100, log of 90 is 1.9542. And log of, let's say, 75 is 1.8751. So what you may notice here is from 10 to the first power to 10 to the 1.5051, you end up going up halfway. This is 1.000 if you want to be really precise. You get all the way up to your 1.5051 within 22 numbers. But then it takes another, 58 numbers to get up to 100. So if you were graphing this, the curve of this would look like this, where it goes up first to about here, very fast movement, but then it slows down, or it starts off fast and continually slows down, but doesn't look slow until it gets up here. So it's not until it gets to about the 50s that it actually looks like it's slowing down. The rate is slowing down, still going up, but the rate, how fast it's going up, slows. And so the logarithmic curves are always sort of like that, although not with that extra little line in it there. Unless, of course, there's transformations to them, but that's the graph look for them. Now, we can do the same thing with a different base number. What I'm going to do over here is I'm going to look at log base 2. So meaning that if I come here to the number 1, that's 2 to the 0 power. The number 2 is 2 to the first power. 4 is 2 to the second power. 8 is 2 to the third power. And every other number in between is able to have its own log. Okay? Now, 3, for instance, is 2 to the 1.58. I don't have the other numbers in here right now, so we'll just keep it there temporarily. And then 5 can be written as 2.2.2.32. Now, something about that in a moment. We'll get into it and using it in the calculator later, but there is a button in the calculator that says log on it. You can only use that for base 10. You cannot use that for 2. Okay, so calculator log button is only for base 10. Other bases use the math button. And another page here will show how to do that. Let's come back here to this 2's. So these are also 2's, and that's 2 to the 2.58 and 2 to the 2.81. Notice that between the 1's and the 2, between 1 and 2, we get numbers that are in between. So from 1 to 2, all the ones in between are 1 point something. Then between 2 and 3, all the numbers in between are 2 point something. So you have a 2, a 2, and a 2 until you get to 3.0. Interesting thing for it. Okay. Notice also that exactly halfway between 2 to the first, 2 to the second, 2 to the third has a 0.58 ending, and the same thing with between 1 and 2. It's a 0.58 ending, exactly in the middle. And those are different from what a 10 would do. All right. That's the other part of a concept of what logarithms are, is think about it as like multiple multiplication, or in other ways, since a power is multiplication many times, logarithms are exponents that, well, it's not quite exactly the same, but it is like, you know, lots of adding becomes multiplication, lots of multiplying becomes exponents, and then lots of exponents, you're now dealing with logarithms. So those are not exactly the same. It's a step up thing. Let's go to the second page here. Now, I told you a moment ago that a logarithmic graph looks like this. And part of the reason is because it's the inverse of an exponential. Inverse of an exponential function. Exponential function. And inverses go over the y equals x line on the graph. So you notice here that these two graphs are these two lines are mirror images of each other over that line. Okay. And this one here is an exponential function. As the exponent goes up, the number goes up. So this would be like 2 to the first, to the first power, to the second, to the third, to the fourth, to the fifth, to the sixth. And it just goes up way fast when you start putting larger exponents. Some information. Important to recognize the difference between logarithms and common logarithms. These are the ones that are base 10. It's common if it's base 10 because that's the most common. Yeah, it is. Back up here, when you have a base that's not 10, that's where you use math and you go to log base. Okay, it's only on TI-84s and newer, not on the 83. Some of the other ones like Casios and HPs will have it. You just will have to look and figure out where the command is to do it. And that would allow you to put in the calculator a base number, and then the number the exponent will make, and then you'll get the answer for that. Try it with your calculator because it will make life much easier. A natural logarithm is different from the others in that it's based on E. Okay, E is a constant. E equals 2.71, and I don't know the rest of the numbers. It's often used in finance and other areas that involve a certain amount of growth every period of time. Now, instead of writing log base E of something, someone somewhere decided to start calling it natural log, LN. Right? So instead, so this is natural log 17. It could have been written as log base E of 17 equals 2.8332. But convention now says that we would use that natural log 17. And it's usually on the calculator, or it's a second function. It's a button, or it's a second function of another button, the natural log. Oftentimes, the natural log is a button, and then the E itself is the second function. I mentioned this already before, customarily written out to 4 decimal places. Now, if you have a calculator that doesn't do the bases, here's the method around it. I told you, where was it here? Yes. On the calculator, you do log base, but if you can't, you use this change of base formula. For instance, for a TI-83 or for a scientific calculator. Because a scientific calculator doesn't have the graphing part of it, but it can do change of base formula simply because when you have a base like that, you can make it log of that base number on the bottom of a fraction and the other one on top, and these become bases 10, which means you can use the calculator key for 10 for the log. Let's make that, I want to make that a better 10. So let's do that. Okay. And if you do that, you get this 2.0437, and you can do it either way, and you would get it correct for this one. Let's look at changing the forms. Now here, when you're in logarithmic form, you can simply take that base number and bring it over to the other side and push that number, that exponent, push it up into the exponent area. Many times people leave the 2 on that side, and they would say 2, bring the 3 over to it, and make it equal to 8. I don't care. They're both true. 8 does happen to be 2 to the 3rd power, which means for this one here, we're going to have 5 raised to the power 6 is equal to 15,625. You can put in the calculator, and you'll see that's true. This way, it's harder to see that 6 is the exponent that makes this number. But put this way, you can see it is. So changing the form will help in some various equations we'll be doing soon. Now, this one was changing from logarithm to exponential. Now we'll be going back the other way. We can go back and forth, and that's what we'll do on the second one. So on this one, log 10 squared equals 100, we're going to do log. The number that's raised to a power is the base. The number we get as a result is with the base, and the exponent goes on the other side. For the next one, we'll do the same thing. This is the base, base 5. The number you're going to get as a result is with it, but the exponent goes on the other side. To process that, and I'm going to do these in the zone. There, got that. It's not completely cooperating, but it is a little bit enough. So good. So we can do something with it. Now we look at the negative exponents. Now you've learned negative exponents. Let's revisit them in this format here, this way of doing things. When you have a negative exponent, it means that you can bring it to the other part of the fraction. Since that's 10 to the negative 3 over 1, we can now, oh, and there's a 1 in front of it that has a power of 1. That 1 is going to stay on top. And the 10 to the negative 3 is going to come to the bottom, but change the sign of the exponent. You can move them back and forth all day as long as you change the exponent each time you move it. Well, 10 to the third power is indeed 1,000. And we can do the same thing with this one, where we then, because of the negative 3, we're going to put the 7 cubed on the bottom. But 7 to the third power is indeed equal to 343, so it makes that fraction. Now let's talk about evaluating it. When you see evaluate a function, you just simply figure out what the amount is, and that means you have to put x here. You have to find the exponent. This is saying evaluate means actually do this. So if you do this in the calculator, or if you do it as a change of base formula, which is sometimes easier to do, so I'm going to do that here. Whoops, that's not the 3 there, it's 10. That's the whole point of doing it. And what you get now is if you put these in the calculator, you'll get about x equals 5, because 3 to the 5th power is 243. However, the other way to do this now, right, now that we have this, okay, what I'm going to do is I'm going to take the 3 with the x. 243 equals 3 to the x. This you've done before, where we have a base 3. If this was base 3, we'd be able to just make the exponents equal to each other. And it just so happens now that that's 3 to the 5th power. 243 is 3 to the 5th, which means x equals 5. You can also get it in the calculator by doing the change of base formula as I'm showing here. Let's look at this one. I am going to do this one with bringing the 5 over here and raising it to that power. So we have 3125 equals, oh, not x, let's do 5 to the x power. So now we have to play with this 3125 and see if it can be 5 to a power, and it is. 5 to the 5th equals 5 to the x. That means x equals 5 is our answer. So that would be the exponent to go here. It's also, if I do 5 to the 5th power here, I can get that 3125. Oh, there, good, got it. Now, let's take a look at evaluating when there's a negative. And how do we know that it is? Well, we don't yet, actually. Okay, I'm going to let this equal to x. I'm then going to do the 1, 10, 24 equals 4 to the x. I'm going to change it to the exponential form. And now I need to make this a power of 4. Well, if it was just 10, 24, I could see that that happens to be 4 to the 5th power. This on the bottom can come up, and it can become 4 to the negative 5 equals 4 to the x. And now we have our answer, x equals negative 5. So this one requires recognizing first that the number is the exponent, and then recognizing that that can become a negative exponent. Okay, very key thing here, that it can become a negative exponent, because sometimes you can have a negative result or a negative exponent. It just means making it fractional. Let's do another one like that. So equals to x. Let's bring that 5 over there. I get 1625 is equal to 5 to the x power. So 625, we're going to get 5 to the 4th power is equal to 5 to the x. 5 to the negative 4 is equal to 5 to the x. So that means x is equal to negative 4 in this case. To use the graphing calculator, use the math key and then go to log base, the arrow key twice, or you can just keep going down in the arrow key and you'll get it too. So you're looking for this A and log base. And if you're not using a graphing calculator, use the change of base formula. All right, so these are, very important graphing calculator reminders, I guess you could say. Now let's look at graphing one of these. Graphing a logarithmic equation. Right? We're going to graph this one. This is the parent function where there are no translations to it. Nothing's changing it. The best way to do these, well, there's two ways. One of them is to use the graphing calculator. But I am going to insist on some type of XY table or something showing you can graph it by hand on some things. I'm going to. Now, logarithmic functions have, since they're going like this, they have an asymptote that they cannot touch. They can come close to it, but not touch it. The way you get that asymptote is you take what's inside the logarithm and you figure out what that equals. Okay, you have to make them equal to 0, and it just so happens that this is 0. Okay, but you cannot have a logarithm of 0. Right, that's something not mentioned yet that I need to remind you. A log of 0 is like dividing by 0. You're not allowed to do it. You can do a square root of 0. That's equal to 0 because 0 times 0 equals 0. But a logarithmic of 0 we can't have. A log 0 we cannot do. So here that means I'm going to have 0 as my starting number and no y because we're not going to graph it. But we can then graph some of the other numbers like 1, 2, 3. If I do the log of 1, I get 0. And if I do the log of 2, I get 0.3. And the log of 3, I get 0.4. Now, what I also need to see is, let's graph that 1 and 0. Oh, I put it in the wrong place there. 1 and 0. I think I'll use the blue one for it. 2 and 0.3 is just barely above it. 3 and 0.4 is just barely above it. I guess about halfway to there. Huh. Now let's try a couple. Let's do way out to 10. So log of 10 is the number 1, which means that this curve is going to be like a very slowly going up, almost like a square root one. However, because we know that x equals 0 doesn't work, and actually better than equals, I need to say x has to be greater than that number. If x is greater than that number, we can't use any of these negatives or the 0. But I want to know where this curve goes. So if I put in place of here, I put some other numbers, like as in, for instance, 0.5, I get the number negative 0.3 for the y. So that means that about halfway here, I'm down to negative 0.3, so I've gone below the line. Well, let's go really close to 0. Let's go 0.1. Okay, so the log of 0.1 is a negative 1. So that means we've gotten to negative, we're right about here. So we're getting down like this, and you may start to see or think about what it is. Let's use like 0.01, which is really tiny. Okay? So the log of 0.01 comes to negative 2. So that means we're going down like this. And now you get the idea that there's a curve here that hugs the line. So now it comes up like this and then goes like that. Right? And this is forever, if we're going backwards, it's getting closer and closer to the asymptote, but never ever actually touching it. You don't need all of these to graph something, but you need enough of them like these to show where the curve is going. Okay, so that's the main, and that's sort of like the minimum, but it might not be 1, 2, or 3. All of that depends upon what this function, and by the way, gives us a good answer. Let's go to another one that's a little bit different. Log base 4 of x. In this case, now we have a base 4. I'm going to do an xy table. And I'm going to see still that I'm going to take whatever is in there and make it greater than or just greater than 0. So that means x's cannot be below 0 and they can't be 0. But I can, so I'll put 0 as my like border with a line there. I'm going to put 0.01 and 0.1 and then 1 and 2 and 3 and 4 and 5. I'll do a few of them here. Well, what do I get when I put them in the calculator, right? So that's going to be log of 0.01 divided by the log of 4. This gives me about a negative 3.3 on the graph. And then I'm going to do log 0.1, or with base 4. And that's giving me about a negative 1.67. No, just 6.7. 1.67 or 1.7. But you can tell that's 2/3 or so. And then it's going to be a 1. So putting in place of this x up here each time. So it's log of 1. And that gives us a 0. Okay, because if this x number is 1, we get a 0. At 2, it comes to 0.5. At 3, it's 0.8. At 4, it's 1. And then we just keep getting up, going up very slowly. So let's graph these. At 0, we can't do it. The 0.1 is negative 3.3. And actually, these, I don't know where we could tell the difference. But the idea is just that they're so close. It's a line that's coming up like this, that's hugging that asymptote. And then we do that at 1, we're at 0, and at 2, we're at 0.5, and at 3, we're at 0.8, and at 4, we're at 1, and at 5, we're a little bit over. So now we curve it to there and continue going and making sense that way. Good curve. And that's matched on these because I put each of them here into the logarithm to use it. And we've got a good graph over here. So I guess that this part is the result. Answer. I'll show it with the marker. Like the one above here, this one was the answer. I want to see an XY table, but now you see how to make it. And you can also do this in the calculator. Remember, you can graph one of these yourself to check to see what the graph is, and then use the table function, and you can make it with decimals for a window. You can come and ask for help to find out how to do that. Okay, now let us graph logarithmic functions that have more going on with them. For this one, for instance, there's a multiplier of 3 here. We're adding 2 to the x, and we're adding 4. So what this one does is stretch it out, and this one's going to move it over, and this one's going to move it up. Actually, the plus means, let's see, plus, minus, yes. It's going to move it, I believe, that way. Everything's going to move over that way, to the left. So we're going to do an XY table just like the other one, because the way to do this is still the exact same method, regardless of all the transformations. I take that log of something, the x plus 2, and the result of it has to be greater than 0. Well, when we subtract 2, that means x must be greater than negative 2, but negative 2 itself, there is no possibility. It would give you log of a 0, which is not allowed. So if I put negative 2 there, I don't have anything I'll use, and that's actually the asymptote. Let's put where x is negative 2 along here. So that means the curve will hug that up or down and then go off. So I am going to get very close to it, negative 1.9. And oh, actually, I want to do it negative 1.99. Negative 1.99 is very close to negative 2. Negative 1.90 is also close to it, but not as much as 99. And then I'm going to put negative 1.01, and I'm actually going to put 5 up here. But it actually doesn't matter. You can put any number. Here are the results that you get for those. For negative 1.99, you get a negative 2. And with a negative 1.9, you get 1. At negative 1, you get a 4 with that, with doing all the parts of this one. At 0, we get 4.9, and then 5.4 and 6.5. Let's graph these up here. I'll put this in red. Negative 2 we can't use, but negative 1.99, as close as I can get, is a negative 2. And then next, it's let's see, negative 2, positive 1. So that means the next one's like right up here, that negative 1.9. Wow, that rose fast. Negative 1 is at 4. Yeah, that's rising definitely fast. 0 is at 4.9. Oh, it just slowed way down. 1 is at 5.4, which would be a little bit like that. And then I went out to a few farther number just to see. 5 is at 6.5. So you see that there's a very big change here. And then it becomes a nice relaxing curve. Okay, let's continue drawing here. Now, the other thing you can do is take the basic one and then move it over 2 and move it up 4 and then condense, or actually the 3 makes it so it's more like that. You could do that. Perfectly fine. You should recognize what those numbers will do, how it will affect it. If you graph it, you can see it. As on the graphing calculators, you can often show the parent function as well, which was let's see. Oh, now I'm getting mixed up. X to the 0, which is 1. X to the 1. So it's going like, no, it's just a little bit. It's this one, give or take. Log X. So it's coming down like this. Okay, I actually going to come back and review the basic one. Okay, here. Oh, it's 0, 1, 0. So actually, let's erase this one. So it's coming up like this. Notice that these are very similar, except that the red one's over and it's up. Right? And it stretches faster, which is the 3 in front of the whole thing. Let's do one more of these. I recommend highly to do an XY table. Try this one yourself. Work on it, pause the video, and then come back here when you have finished it. And I will go through it with the XY table. Welcome back. I take this part first, x minus 1, and I say that has to be greater than 0. So now add 1, x is greater than 1 or equal to 1. 1 is here and we can't use it. But I can do slightly larger than it, 1.01, 1.1. Then I'll do 2, 3, 4, and 5. Don't need that many maybe, but it does help me be more secure. If I put 1.01 into here and subtract 1, it would be log of 0.01. And then figure out that log, multiply by negative 2 and subtract 5. We're going to get is about negative 1. With a 1.1, I'll do the same thing, and I get a negative 3. 2 is a negative 5. 3 is a negative 5.6. 4 is a negative 5.95. Then we're at negative 6.2. Oh, boy. Okay. Let's graph these. So first, the asymptote is that 1. So we know we cannot touch the equals 1 line. Also, greater than 1 is also the domain, because those are the only x's that are allowed. At 1, we can't do anything. It's on the asymptote. But at 1.01, we can do that. It's down at negative 1. So you can't really see the 0.01 very well. 1.1 is not much better here, but it's down to negative 3. Oh, we're going down. What's up with this? At negative 3. At 2, we're down to, oh, I made a mistake over here in my writing, and that should be a 5. I used something looked off right there, look around there. So let me put these points a little better here. 1.1, 1.1 is at negative 3, 2 is at negative 5, 3 is at negative 5.6, 4 is at negative 5.95, 5 is actually beyond it at negative 6.2. So we have a curve coming here, and if you keep curving it, it appears that we would get to this, which would be, well, actually continues going. It continues and continues and continues, much better than I'm doing. And here it's hugging the asymptote line. So now what's happening is it's been switched, it's been reversed. This one is a normal curve like that, but it's a positive number in front. This one has a negative number in front, so that basically flips it over. The best way to ascertain that, or any of these changes, is to literally simply do an XY table, and then just put in a few numbers selectively. I am also going to show that in yellow too, close enough. All right, so this will help you with graphing these because you will see some graphing log functions in the future, like in exams. I hope this was helpful to understand how to do these. Thank you for watching and listening.